1D, 2D, 3D, 4D. These are all types of data storage.
Cassette tapes can be unwound or stretched. The magnetic particles in VHS tapes gradually lose their charge, creating static. CDs are easily snapped or scratched. Blu-ray discs have a limited storage capacity.
What now? The future of data storage. So let's go back to CD. Regular discs work using binary code on polycarbonate plastic. The dots represent ones and zeros, and the data is received by the reader based on the reflections. The difference between traditional discs and 5D discs are the layers, or in other words, dimensions.
So, what is a dimension? Measure in a single line, breadth, height, thickness, or circumference. How do dimensions apply? 5D discs have 3 layers of data, as previously mentioned, and not 5. It is 5-dimensional because data can be retrieved based on 3 aspects: the location from which data is retrieved, the strength of the light, and lastly, the orientation. This is how a reader would see the nanogratings, or bumps engraved on the disc. This is how the layers would be perceived.
Here's another example. 2 separate pictures can be viewed at the same time when overlapped, but under different conditions, they can be viewed separately. This is how the layers of data on a 5D disc work with respect to light and orientation. Here's a timeline going from 2009 to 2016, where 5D discs first appeared. In 2009, a femtosecond laser was first used on silica glass and applied to data storage. In 2010, the short pulse on a femtosecond laser was decreased to 1.5 times 10 to the negative 6 seconds. In 2012, the optical microscope was first used in 5D storage. With the creation of new technology comes new barriers and challenges with development. The cost of a short pulse femtosecond laser is approximately $500,000. Not only is it expensive to produce the discs, but also to read them. A 5D disc reader is also difficult to obtain, making it nearly impossible to widely distribute the technology effectively. Currently, Professor Kazansky and his crew are looking for partnership to mass-produce 5D discs.
Because 5D discs are made of a thick silica glass, they can successfully retain information for up to 13 billion years. That's as old as the sun.
Whoa! The reason why it can store data for so long is because the layers of information are sandwiched between the glass. In addition to being durable, 5D discs can store up to 360 terabytes of information because of the multiple layers of data. 5D discs can also withstand up to 1,000 degrees Celsius.
If you were under that heat, you would die in 18 seconds.
So, what did we learn? We covered how 5-dimensional discs compare to traditional discs, defined dimensions and how it applies to the concept using our own laser and layers setup. We also covered methods of production and the barriers to development. And finally, showed how 5-dimensional storage can impact today's society. Our opinion. Well, We think that 5D discs are a breakaway to the future. Right now, CDs aren't used often, so you might still be questioning whether the 5D disc would be useful. But just imagine these discs as a part of a computer, your iPad, or maybe tablet, your iPhone, or maybe Android. Anyhow, 360 terabytes of storage. With 5D discs, you can store libraries of video games, music, photos, and save space at the same time. While 5D storage is a major technological breakthrough that requires experience, there are lots of other ways to spread knowledge to your community, like making a video, for instance. Will the next breakthrough come from your school? What can you do to make an impact?
Catherine Burzak, 2009, May 20, retrieved May 11, 2017. Bivali, May 01, 2017, retrieved May 11, 2017. Swinburne University of Technology, Australia, 2017, retrieved May 11, 2017. Eternal 5D data storage could record the history of humankind. University of Southampton.np, 18 February, 2016, web, 21 May 2017. Storage technology developed for fused silica glass to record and read digital data in the order of CD recording density. Hitachi.np, 24 September, 2012, web, 21 May, 2017. Khalid Pali, Deepak L.N. Ali M. Al-Shiri, Daniela T. Marquez, Lucas Andrzejewski, Juan C. Ciano, and Ravi Pujarwa. Ultra high density optical data storage in common transparent plastics. Nature. Scientific reports. 2017. Web. 21 May 2017. Murphy, Douglas D. Kenneth R. Spring, Thomas J. Fellers, and Michael W. Davidson. Principles of birefringence. Understanding waveplates. Edmund Optics. NP. 2017. Web. 21 May 2017. Joe Merchant, 2016. Retrieved May 11, 2017.